So, hello, welcome to the last week of classes. The next to last lecture, we are nearing the end and we're ending it with chemical reactions. Because, we might as well, if we're going to end this class, end it with file. Kill it with file. Um, yeah, so we are gonna cover new material this week. We are gonna do these chemical reactions. I've already talked about this, that you have a homework due Wednesday from chapter 11. Chapter 12 homework is actually going to be due on Sunday because I'm an asshole. However, you do have a final on Monday, 1 week from today. In fact, 1 week plus a half hour from right now is your final. Before we get started on that note, I want to remind you that I did plan a review session. Your review session will be Friday, May 7th at 3 o'clock. During that session, I'm going to go through last semester's final. If you cannot make it or / don't want to make it, I will be posting it to YouTube. So I'll film it like always and post it like always. Um, any questions about that stuff before I get into chemical reactions? Okay. That's also when I'm going to post the solutions to the last semester's final is Friday at 3. So let's get into it. See, what we're going to talk about, as I said, is chemical reactions. And so it's worth pointing out what that actually means before I get into them. Here's the general idea. We can talk about all properties of any material. And for any material, we can say it has physical properties and chemical properties. And the short version of this is chemical properties is just, does this chemically react with something else? Everything else is physical. If you talk about the boiling point of something, that's a physical property. The density of something, that's a physical property. The color, the specific heat, if it does it dissolve in a liquid? Chemical properties are just, hey, if I mix this liquid with that liquid, does it burst into flames? That's a chemical property. If I mix substance A and B, do they react? That is the only thing that is a chemical property. And that actually gets into what is a chemical change versus a physical change. You see, anytime you mix two compounds, it'll either can have a physical change or a chemical change. A physical change means they actually just mixed. You know, if I take this ruler or the slinky and pull it, I've stretched it out. That's a physical change. Anytime you change the shape or even the phase, if you boil water and you turn water into steam, that's a physical change. A chemical change is anytime a chemical reaction occurs. And a chemical change means there has to be a new chemical formula. You see, boiling water is a physical change because it goes from liquid H2O to gaseous H2O, but it stays as H2O. That's physical. Chemical change means the actual composition is different. That if I take hydrogen peroxide, H2O2, and remove an oxygen to turn it into H2O, we're going to talk about that later, that would be a chemical change. Now, there's actually kind of simple ways to recognize whether or not a chemical change occurs. Anytime a chemical change occurs, one of four things will happen. Now, I'll say for the record, it might be more than four. Like, it's at least one of these four things happen. More than them can happen. And they are as follows. Anytime gas bubbles start forming, that means a chemical change occurred. It means a gas is being released. Like Alka-Seltzer tablets, chemical change. You are changing a chemical setup. This is a picture of calcium in water. Also, anytime heat or light is produced, if you mix substance A to substance B and it blows up or bursts into flames or just gets hotter or gets colder, that's rare but happens, that is proof of a chemical change. This is sodium in water. But it also just means like a hand warmer thing that you crack it and it gets warm. That's a chemical change. It also can be anytime there's a solid is formed by mixing liquids. If you look at this, it kind of, you can tell, go from a liquid to this grayish stuff is a little more solid. It kind of fluffs up. If you mix two liquids and get a solid, that will always be a chemical change. And the last one is a weird change in color. If you watch this GIF, they have a clear liquid and a yellow liquid. They mix clear and yellow and get blue. Now, if you mix yellow paint and blue paint and get green paint, that doesn't count. But if you mix clear and yellow and get blue, yeah, that sure as hell counts. Same way with the GIF in the bottom left that I'm mixing clear and peach-ish and getting gray. Weird color changes. Oh, it was a chemical reaction. And so at least one of these four things were happening to have a chemical reaction. Bubbles produced, heat or light, getting a solid out of liquids, and color changes. Questions so far? Now, when we talk about a chemical change or a chemical reaction, what we're going to do is we're going to talk about the chemical reaction in terms of the chemical equation. And the chemical equation is just a way to use symbols and formula to describe exactly what happens. And it's always going to be written as something arrow something else. Now I have a plus B yield C plus D. It's of note that sometimes there might be only one thing on the left, only one thing on the right, or there might be more than two things. But the general idea, it'll always be reactants, yield, products. Whatever's on the left of the arrow, which, side note, the arrow is actually called the yield sign because it's saying what it yields, is called the reactants because that's what reacts. Whatever's on the right side of the yield sign is called the products because that's what you produce. And when you write them, you just put the chemical formula for all the reactants, an arrow, and then the chemical formula for all the products. The only real other bit of complication, well, there's two bits of complication, but the first one is you should always write your phases. You will write your phases by writing them in parentheses, a symbol, S, L, G, and AQ. Well, S stands for solid, L stands for liquid, G stands for gas. AQ isn't actually a phase, but it's very important in chemistry. AQ stands for aqueous solution. That's anytime you dissolve something in water. So if you have like salt water, that's NaCl AQ. AQ just means you dissolved it in a liquid. And so you'll always put reactants with their phases, a yield, their products with their phases. Any questions? I am tired. Okay. The only other thing that might come up is there might be something called a catalyst. I'm going to talk about catalysts in more detail later on today. I'm going to come back to them. But for now, what you should know is that a catalyst is something that might speed up a reaction, that it just makes it go faster, but is something that is not used up, that it doesn't, the reactants all turn into the products. The catalyst starts with existing and ends still existing. Of note, whenever you have a catalyst, you normally write that above the yield sign. As I said, we'll talk about these more in general detail later on, but just know if you have something above the arrow, that is a catalyst. Sometimes the catalyst is a heat. If heat is the catalyst, you just put a triangle over the yield sign. But that's the general idea. You just write whatever you have with plus signs between them as the products, a yield sign, and whatever you end up with plus signs between them, marking if it's a gas, liquid, solid, or aqueous solution. This equilibrium thing we're never going to talk about, so you can ignore that. Good so far? Any questions? Now, in a chemical reaction, what happens is three things occur. And we're going to watch a chemical reaction that someone animated on top of because it's hilarious that way. The first thing is the reactants disappear. that whatever you had as reactants, they get used up. They're going to go away. As the reactants disappear, in this case, the reactants is this black powder. This black powder is being used up. What happens is a new substance will appear with different chemical, probably different physical properties. That is here, these weird tentacle arm things coming from my devil guy here. Because yes, I love the fact that someone put a face on this. That's something new that's be created and coming. And lastly, there will be heat, light, electricity, sound, some form of those, either released or absorbed. It's not always noticeable. Sometimes it's so small you can't notice it. But I mean, take a look at this one. It lit on fire. Lighting on fire is heat produced. Quite a lot of heat produced. So you can see it. And so we use up the black powder. We make those tentacle arms. We have fire. There it is. Reactant being used up. New substance produced. Heat produced. Okay? Now, to show you your first chemical reaction in writing form, it's going to look something like this. And what it is it'll just give the chemical formula for each compound that you start with and you end up with. And it says exactly what happens, once again, including the phases. See, what this says is if you have, and let me make this show up first, and then I'll do it. It says if you have aqueous sodium chloride and add it to aqueous silver nitrate, it will yield aqueous sodium nitrate and solid silver chloride. I wrote silver chloride precipitate. Don't worry about that word yet. In fact, it shouldn't be there yet. That's the general idea. It says exactly what happens. And as long as you can read chemical formula, which we covered last chapter and the chapter before, you know what happens. NaCl plus AgNO3 yields NaNO3 and AgCl. Okay? Now, it's of note, as we talked about last chapter, metal cannot be created or destroyed. Take a look at this chemical reaction on the bottom. It says H2 plus Cl2 yields HCl. It says hydrogen gas plus chlorine gas makes hydrochloric acid, gaseous hydrochloric acid. This is a real chemical reaction, but as written, it doesn't make sense because it says if you have two hydrogen atoms and mix it with two chlorine atoms, you get one hydrogen atom and one chlorine atom. This violates the law of conservation of mass. Because if I start with two hydrogen atoms, I must end with two hydrogen atoms. If I start with two chlorine atoms, I must end with two chlorine atoms. Anytime you write a chemical equation, you must make sure it is balanced. What that means is you have the same amount of reactant as you have product. Different forms, but you have the same number of atoms. That if you start with two hydrogens, you end with two hydrogens. If you start with two chlorines, you end with two chlorines. Now, you can't just change the chemical formula. It would be nice to say, okay, instead of HCl, we get H2Cl2. That's two hydrogens, that's two chlorines, there we go. But H2Cl2 is a different formula than HCl. And honestly, H2Cl2 isn't even possible to exist. What you're going to do is you're going to put coefficients in front of terms. And so they balance. That if I say H2 plus Cl2, that'll just give me 2HCl. What that does is it gives me two hydrogens, two chlorines. And when you balance an equation, you just make sure you have the same amount of each element individually in the reactants as the products. And if you do not have so, you'll just put these multipliers in front. Okay? Still good? My quiet class. Okay. Of note, you cannot change the subscripts. That's what makes what the compound is. You can only change the coefficients. And coefficients cannot go inside terms. I couldn't be like H2Cl. It's HCl. It's HCl. It's not going to be anything but HCl. I have to put it in front. Now, in general, when balancing, always make sure your chemical formula is correct first. If your reaction is wrong, it may be impossible to balance it. So make sure your chemical formula is right. And once again, the subscripts cannot be changed. This is another chemical formula that hydrogen gas plus oxygen gas can be made to form water. It's done with electricity. If you put electricity in it, it can happen. I can't make it anything but H2. I can't make it anything but O2. And I can't make it anything but H2O. But when I balance, what I can do is I can put numbers in front of it. See, what I can do is I can look at this and say, right here, right here, I have 2 oxygens. Right here, I have 2 oxygens because there's 2 H2Os. Oops. Right here, I have 4 hydrogens, 2 H2. Right here, I have 4 hydrogens, 2 H2. That is balanced. So of note, you don't write ones. If anything isn't there, you assume it's a 1. So it really should be 1O2, but you don't write that ever, like at all. It's not necessarily incorrect to write your ones, although it's kind of incorrect to write your ones. You shouldn't. Sorry, woke up early today, so I keep yawning. But that's going to be the general idea. You just put these numbers in front so you have the same amount of each element before and after. So I'm going to jump into an example, a kind of complicated example, but an example. But is there any, because it's kind of one of those things that I think it would make more sense knowing how to do once I do it. We good for me to try one? Okay. So here's an example. Aluminum plus oxygen can lead aluminum oxide. This is rust, aluminum rusting. The aluminum oxide is just rusty aluminum. But if you have aluminum, mix it with oxygen gas, you can get aluminum oxide. If I just write this formula, what I'll do is I'll count how many of each thing. Al, there's only one there. O2, there's 2 oxygens. Al2O3, that's 2 aluminums, 3 oxygens. Now it'd be nice to say, shouldn't just Al plus O2 just lead to AlO2? I mean, that would be nice. Then it would be balanced. But before I get into balancing, we know it has to be Al2O3. The reason, though, we have to have Al2O3 goes back to last chapter. That Al2O3 is a mixture of aluminum and oxygen. And if I look at aluminum and oxygen, well, aluminum is right here on a periodic table. Aluminum's a metal in family 3A. That means aluminum has 3 valence electrons. That means aluminum has a charge plus 3. Oxygen is right there. Oxygen's a nonmetal with 6 valence electrons. 6 minus 8 is -2. That means oxygen has a charge -2. And so if I mix aluminum and oxygen, an Al plus 3 and an O minus 2, I'll have to use that cross method. Take that 3, drag it down. Go. Take this 2, drag it down. Al2O3. That has to be the formula. But that isn't balanced. Just knowing that's the formula is well and good, but we need to take care of balancing it. So that was review from last chapter. Let's actually balance it. If I'm going to balance it, what I'm going to do is I'm going to count how many I have on each side. 1 Al, 2O on the left. 2 Al, 3O on the right. It's not balanced. And what I'm going to do is I'm going to try to match things. This is actually a very complicated example. I'm starting you out with one of the HODL problems because I'm an asshole like that. What you're going to do is you're going to multiply by whole numbers. You can never multiply by a fraction. And you multiply by whole numbers until they are the same. Now, if I want to get oxygen the same, I have 2 on the left, 3 on the right. There is no whole number I can multiply 2 by to get 3. And this whole number I can multiply 3 by to get 2. But what I could do is multiply my left by 3 and my right by 2. If I do that, they both have 6. And what I'll do is I'll put a 2 in front of my aluminum oxide. By putting a 2 in front of my aluminum oxide, I now have 4 aluminums and 6 oxygens. I'll then put a 3 in front of my oxygen. That gives me 6 oxygens. And now my oxygen is balanced. I still have 1 aluminum on the left, but I have 6 oxygens on the left. And I now have 4 aluminums on the right, but I have 6 oxygens on the right. My oxygen is balanced. I mean, it's still not right because my aluminum isn't balanced, but I can do that. My left has 1 aluminum, my right has 4 aluminum. How do we turn 1 into 4? By multiplying by 4. And this shows me 4 aluminums on the left, 4 aluminums on the right, 6 oxygens on the left, 6 oxygens on the right. That is the balanced equation. Questions? It's going to come up a lot on this last chapter, so I'm going to do 2 more examples though. Okay. Before I do, yawning so much. Before I do 2 more examples, once again, always have to use whole ratio. I can't say H2 plus a half O2 is H2O because I won't have half an O2. Something like a fraction can never be though. It's going to be 2H2 plus O2 yields 2H2O. Some other tips, once you're done, make sure that the numbers have the same amount of atoms. Always count. There is 4 hydrogens, there is 4 hydrogens. There is 2 oxygens, there is 2 oxygens. My only other hint is that if an element is in multiple places, save it for the end. The order you balance your elements in doesn't matter, but just complicated ones wait. My second example, I'll show you what I mean though. I guess my third example. So let's do another one. Here's a chemical reaction. Lead nitrate plus potassium iodide leads to potassium iodide plus, lead nitrate plus potassium iodide leads to lead iodide plus potassium nitrate. I misspoke. What I'm going to do is I'm going to count how much of each element. Pb is lead. There's only one of them. Nitrogen is in parentheses. There's 2 nitrogens. Oxygen is 3 times 2. There's 6 oxygens. 1K, 1I. Over here I have 1 Pb, 2 I's. 1K, 1 N, 3 O's. And so I say that's what I got. And what I'll do is I'll look for what's not the same. My lead is balanced. Both sides have 1. My nitrogen, left has 2, right has 1. My oxygen, left has 6, right has 3. My potassium's good. My iodine isn't. It doesn't matter the order you do things in. But what I'm going to do is I'm going to pick one of those 3 unbalanced elements, nitrogen, oxygen, iodine, and I balance it. I chose to start with iodine. Why? I felt like it. It was the last one I wrote. No other reasoning. And what I'm going to do is say my left has 1 iodine. My right has 2. I need those to be the same. If I have the number 1 and I want the number 1 to be 2, I multiply by 2. And so what I'll do is I'll put a 2 in front of my potassium iodide. What putting that 2 does is it goes from 1 iodine to 2 iodine, and from 1 potassium to 2 potassium. Now this might seem like 1 step backward, 1 step forward, 1 step back, because I had potassium balance and now it isn't anymore. That's fine. That happens a lot. You just keep working on it. Because now I can say, hey, let's look at this. I just fucked up my potassium. I have 2 potassium on the left. I have 1 potassium on the right. I want them to be the same. How do I turn 1 into 2? I multiply by 2. If I want these potassiums to be the same, I'll put a 2 in front of my KNO3. By putting a 2 in front of the KNO3, I now have 2 Ks. This also doubles my nitrogen and also doubles my oxygen. But that's a good thing. I needed to double them anyways. And now I have 1 lead both sides, 2 nitrogens both sides, 6 oxygen both sides, 2 potassium both sides, 2 iodine both sides. This is a balanced equation. Questions? Okay. I'm going to do one more that's going to look really complicated. It's a little complicated, but it's not that bad. Take, for example, this guy. Aluminum sulfate plus barium nitrate turns to barium sulfate and aluminum nitrate. If I want to start counting how much are each thing, something you might notice is there's a shit ton of oxygen here. Oxygen's in every single term. I said before, it doesn't matter where you start. Here's the exception. If an element is in multiple places, put it off. Ignore it as long as possible. So what I can do, and I'm going to draw all over this, is I'll say, okay, we have 2 aluminums. I have 3 sulfur, because the parentheses in the 3. This right here is 12 oxygen. 1 barium, 2 nitrogen. And this right here is 6 oxygen. So I have 12 oxygen plus 6 oxygen, that's 18. On the right, 1 barium, 1 sulfur, 4 oxygen. 1 aluminum, 3 nitrogen, 9 oxygen. 4 plus 9, 13 oxygen. You all follow how I got those numbers? I assume you're good because no one asked any questions, but. So I'll do the same idea. I'll pick something that's off to fix. That something won't be oxygen because it's everywhere. It's complicated. Let's ignore it. But I'll pick something else, like, I don't know, aluminum. And say my left has 2 aluminum, my right has 1. I need to double my aluminum. And so what I'll do is I'll just shove a 2 in front of that term. I cannot put it in that term, in front of that term. Nothing on my left changes, but on my right, I now have 2 aluminum. My sulfur didn't change. I now have 6 nitrogen. My oxygen, well, let's see. This is still 4 oxygen. This oxygen is 3 times 3, which is 9, times 2, which is 18. 18 plus 4 is 22. And I say, okay, cool. That is balanced. What is it? Well, nitrogen isn't. Let's do that next. I have 2 nitrogens on the left. I have 6 nitrogens on the right. I want them to be the same. How do you turn 2 into 6? You multiply by 3. That will triple my nitrogen, but it will also triple my barium. It'll also, barium nitrogen, will also add more oxygen. Won't actually triple it. Because my oxygen here, this is 12. This is 3 times 2, which is 6 times 3 is 18. So I have 30. And I'll say, okay, that messed up my bariums. Let's do them next. 3 bariums on the left, 1 on the right. So I'm just going to multiply my right by 3. That'll triple my bariums, triple my sulfurs, and give me an extra 12 oxygen. Sorry, that's a lie. Give me an extra 8 oxygen. Because 3 times 4 is 12, and then 9 times 2 is 18. 18 plus 12, 30. And look, we're balanced. The same amount of each thing on both sides. That is the balanced equation. Questions? This makes sense because you're going to be doing a shit ton of them. There's a bunch on the homework just balancing, and then the rest of this chapter, or most of the rest of this chapter, is going to be predicting the reactants in a chemical reaction. And once you predict the reactants, you're going to have to make sure you balance it. I would say speak now if ever hold your peace, but really no. Speak now, or if you have questions later, ask me later. Okay. This covers the products disappearing, the reactants coming. Sorry, that's backwards. The reactants disappearing, the products coming. This covers that bit of the reactions. This does not talk about the energy. That I said in a chemical reaction, there's a change in energy. All chemical reactions have some change in energy. It's not always noticeable or visible, but there's always some. The reason why is energy is needed to break bonds, and energy is released when bonds are formed. But conservation of energy says all energy comes from somewhere. That energy cannot be created nor destroyed. Now, some experiments. Sorry, I want to check something. Where did I put that? I just want to make sure I didn't mess something up. Okay. Some reactions will produce heat. A reaction that produces heat is called exothermic. Some reactions absorb heat from their surroundings. Reactions that absorb heat, which are much rarer, are called endothermic. But the general idea is there will always be some energy gained or lost. And that energy gained or lost would just be taken from the surroundings. What really happens is there's really an energy curve. Take, for example, if you burn methane. Or you burn natural gas. Sorry, not methane. Oh, yeah, methane. Yeah. If you burn methane. When you burn methane, it doesn't just burn on its own. You have methane that just sits there. You turn it on fire, reaction happens. It burns on its own. What happens is that when methane burns in the air, what is happening is the methane is reacting to oxygen. And what's happening is you're going from having some CH4 and O2 and turning into CO2 and H2O. And it's releasing heat. It burns because it's releasing it. You need a spark to start it, but once you start it, it produces more heat than you needed to start it. That spark to start it is called the activation energy. The activation energy is the energy needed to acquire it. What it is the energy required to break the initial bonds. The energy required to have the hydrogen break free from the carbon and the oxygen to break free from each other. That's the spark when you light this thing. And so what we'll say is the activation energy gets it going. Once the activation gets it going, it'll then bond together. And when it bonds together, it'll have less energy than it started. Some of that energy will go towards keeping it on going. It'll go to keep supplying the energy, the activation energy for the molecules that haven't reacted yet. But all the rest will go by heat and light. That the blue flame will glow and get hot because we're releasing more energy into the air. Okay. Do I have K? Yeah, no, I'll do that later. Okay. Thermite is an example of this. Thermite is a mixture of rust and aluminum, iron oxide and iron 2 oxide and aluminum. It would just be fine if you sit there, but if you light it on fire, that gives it some activation energy. Once you get the activation energy, it burns much, much brighter, much faster. I mean, this wick is now lit. It has like a small fire. That's just the wick burning. But once the reaction occurs, boom, there we go. It's hot enough to melt through steel. That's because you have to add some fire to get the activation energy, but then the chemical reaction occurs. It's of note if you need to add heat as activation energy, that means heat is a catalyst. As I said before, I'll put a triangle over the yield sign. But yeah, this is an exothermic reaction. It gets hotter than it started. It produces a shit ton of heat. In an endothermic reaction, you pull heat from your surrounding. So if you try to mix nitrogen gas and oxygen gas, you can get nitrogen monoxide. It does take heat to do it, to get the action to start, the activation energy, to break the nitrogen oxygen apart. But once they bond together from N2 and O2 to NO, it's going to have less energy. What that means is it's going to pull heat from the surrounding. This works for cooling things, that if you do this reaction and touch it, it'll feel cold. It'll feel cold because it'll suck heat out of your hand. These are, as I said, a lot less common endothermic reactions. Most reactions are exothermic, which is just more fun because, you know, lighting shit on fire is always fun. All right, we can also talk about how quickly reactions work, how fast they happen. The rate of reaction occurs depends on a whole bunch of stuff. One is temperature. Almost everything, the hotter it is, the faster the reaction occurs. That's because cold things have slow-moving molecules. Hot things have fast-moving molecules. Fast-moving molecules bump into each other more often. Reactions happen faster. Also, concentration. That if you try to burn phosphorus in 21% oxygen air versus burn phosphorus in 100% oxygen air, it'll happen faster if you have more concentration. It's not diluted. Surface area, how much of the stuff is touching. There's just like a tiny bit is touching. It's not going to happen very fast. If you grind it up, and if you grind it up so that it can mix together freely, it'll happen faster. And the last one is a catalyst. I said before I'd come back to these in detail. I'm doing so now. A catalyst is something that speeds up a reaction. And what it is, it doesn't, it's not a reactant and not really a product because it doesn't get changed. It starts as something, it ends as the same thing. It just makes the reaction happen super fast. The reason why is because I kind of quasi lied there. The catalyst is a reactant and a product. It just stays there in the end. Take, for example, this idea. Sulfur dioxide and oxygen can produce sulfur trioxide. And it's a very slow reaction. But if you add a nitrogen monoxide, it happens super fast. It's because nitric oxide is a catalyst. It speeds it up. Wait, there's no mistake though. Sorry. I should say nitrogen monoxide. I'll have to fix. I don't know why I wrote nitric oxide. It's some people call it nitric oxide. Nitrogen monoxide, nitric oxide is the same thing, but I want to do the official naming. The reason why is that two reactions happen quickly. The first is the nitrogen monoxide is going to mix with the oxygen. When nitrogen monoxide mixes with oxygen, we're going to NO2. But once that reaction occurs, we now have some NO2. And the NO2 will see the SO2, and they'll react. And the NO2 and the SO2 will produce 2 SO3 and 2 NO. If I put these together, if I say all of these are my reactants, all of these are my products, I'm left with SO2 plus 2NO plus 2NO2 plus O2 yields 2SO3 plus 2NO plus 2NO2. And I wrote 2NO twice. Sorry. How have I never noticed that before? That shouldn't be the second time. And if you look at this, I started with NO2 and I ended up with NO2. So it's like it wasn't there. It's like it didn't react. It did, it reacted and disappeared, but it started and ended with it. I started with NO and I ended with NO. So it's the same thing with that too. I really was just like I had SO2 and O2 turn into SO3. That's what makes it a catalyst. is that it didn't really react. It started and ended the same. Well, it did react. It really did react, I should say that. But it broke right back down and came right back together. Okay? Let me show you an example. This would be done in person if we were in person. Hydrogen peroxide is H2O2. If you take hydrogen peroxide and let it sit, it'll decompose on its own. H2O2 will turn into water and oxygen. It is exothermic. It does heat up when it happens, but it takes a long time. However, this has a catalyst as potassium iodide. If you add potassium iodide, what happens? This reaction happens super, super fast. Now, I want to point out again, it's exothermic, produces heat. So slowly, this will just slowly lose oxygen. When it happens quickly, you very suddenly make hot water. What I'm going to do is I'm going to do this reaction, and I'm going to mix in dish soap. Oh, started right away. So what I have here in this beaker is hydrogen peroxide and dish soap with some food coloring just to make it interesting. What happens is I am going to very, very quickly make hot water, but there's dish soap in. Because there's dish soap in it, it's going to suds up. And in that little thing in my hand is potassium iodide. When I add the potassium iodide, the reaction happens quickly. It suds up near instantly. And you can see steam coming off it because it's exothermic. It gets super hot. But all that is something that makes the reaction happen really, really fast. Hell, if I put it in a different beaker, I can make it actually shoot out of it if I restrict the neck. First time I tried to do that, I covered the ceiling of the room and decided not to try it anymore. Okay. Okay, we good so far? I got 8 minutes left. Okay. That's all chemical reactions in general. For the next big hunk of this chapter, and today and Wednesday, I'm going to talk about some very special types of reactions. And I'm going to talk about 5 different types of chemical reactions. Combination, decomposition, combustion, double replacement, and single replacement. I'm only going to get to the first 2 today. I might only get to the first 1 today, but we'll see. And we're just going to say how these reactions are and how you can predict their products. What is a lot of these chemical reactions is I'm going to tell you the reactants, and you are going to tell me the products. That's how problems are going to work here. And if you know what type of reaction, I always say what type of reaction, they're normally pretty easy to predict. So let's start with combination. Combination is anytime you take 2 or more reactants and combine them to make one product. Take, for example, lithium and oxygen. If you mix lithium and oxygen, you get lithium oxide. That is this weird white pieces it has after the reaction. So I'm checking to see if I have a video of one of these. Okay, no, I don't. This is a single replacement that lithium plus oxygen yields lithium oxide. Here's another one. Sodium plus chlorine yields sodium chloride. These are normally exothermic. They normally produce a lot of heat. But it's just you take your 2 things and put them together. And they're pretty easy to predict. The trick here is, Na plus CO2 isn't NaCO2. And Li plus O2 isn't LiO2. The trick here is watch your ionic charges. When you put them together, what you should do is think about what they're made up of. For my example here, what I would say is if I just gave you the reactants, I would say you're mixing lithium and oxygen. Lithium is a metal in family 1A. That means lithium has a charge +1. Oxygen is a nonmetal in family 6A. 6 minus 8, -2. That means lithium oxide is Li2O. When predicting these, always go back to your ionic charges. Watch your ionic charges, and once you have your ionic charges, figure out what the compound is. Once you have what your compound is, then you can worry about balancing. but that is how you predict a combination reaction. Okay? A decomposition reaction is the opposite. A decomposition reaction is anytime you have one thing and it breaks into parts. Say I got mercury 2 oxide. Mercury 2 oxide with a little bit of heat will break down into mercury and oxygen. That's a decomposition. If I have water and put electricity through it, if I put electricity through water, I get hydrogen and oxygen. That is a decomposition. That elephant toothpaste thing, this guy was taking hydrogen peroxide and turning hydrogen peroxide into water and oxygen. Right? Its chemical formula was this. Oops. Was this. That's a decomposition. A decomposition is you start with one thing and break it into parts. Here's a cool one. Mercury 2 cyanide, when its decomposition reaction looks like this. That it makes what looks like weird Lovecraftian hollow tentacles when you light it on fire. Decomposition reactions are not predictable. I am never going to be able to give you the reactant and ask for the product. They are predictable, but you need a lot more chemistry. Let's put it that way. I am never going to ask you to predict them. Just know that decomposition is taking one thing, breaking it into parts. But you will have to, I'd have to give those. Combination is I will give you the reactants and ask for the products. Okay. Okay. I'm going apparently a little fast. I'm 4 minutes ahead where I should be, but no one is telling me to slow down or ask questions, so I assume we're doing fine. I'll just stop there anyways, though, and we can pick up on this on Wednesday, which will be our last class. Woo! Minus the review session. So we'll leave there. Have a good day, and I'll talk to you all on Wednesday.